Welcome everybody. We continue with differentiation and now graphing derivative. Last I said this one. Graphing derivative. Our subject is now this one. What can we learn from a graph of f of x? What does it mean? Let's write it. What can we learn from a graph of f prime of x? Yeah, first of all, rate of change of x. We can learn the rate of change of x, that is maybe it is positive, negative, or zero. And another thing, rate of change itself, that is increasing or decreasing. Yeah, let's put a graph here now and show these things as a tangent lines. So we have a graph like that. Here we have a slope, and here like that, and like that. Now, here we have a tangent line here at point A, and another tangent line at point B. Here another tangent line at point C, and here another tangent line at point D. You see it is also parallel to the x-axis, and we have another tangent line here and at point E. You can easily see that at this tangent line we have a parallel to the x-axis. So here's the x-axis. So slope is 0, and at the same time also at the point D, slope also is equal to 0 and is parallel to the x-axis. The difference of B and C points are, one of them is more decreasing, that is, say that slope of this point is minus 4/3, and this slope may be minus 1. Yeah, this one is bigger and the other one smaller than this one. And the point for E, you see these are B and C are decreasing. So slopes bigger than 0, that's positive, smaller than 0, that is negative. By the way, on the other way, on the E point, slope may be equals 2, so this is increasing, and slope is positive. So you see these are the tangent lines, so you can understand that from the tangent lines and the slopes, they are whether they are decreasing or increasing, or the positive or the negative, maybe 0 also. So it's importance of derivative of the function. So next, we have now differentiation rules. We continue with differentiation rules. First one, say differentiation rules. Say rule 1 is derivative of a constant function. Let's give a definition for this one. If f has the constant value fx is equal to c, then df over dx, that is derivative of f with respect to x, we said it before, and or d over dx, the function is c, so it equals 0. We have to know this one. And as an example, we can give some of thing, and this is fx is equal to 8 maybe, and derivative of f prime x, or df over dx, or maybe d over dx, 8, you see, is equal to 0. Also, we can give another example. We don't have to write integer here as 8 for the question. This may be another example, maybe minus pi over 2. Also, again, we have f prime x, I mean derivative of the fx function is equal to, again, 0. It's not important because this is constant, so as 8 or as c, so it's not important whether it is pi over 2, minus pi over 2, minus e, whatever. The derivative of the function is equal to 0. Now, the proof of this rule is easy one, so I want to give one proof. Maybe it's better to understand by the limit also. I only give this proof of rule, and the other rules, I don't give any proof. Proof of rule 1. Say if f of x is equal to c, you know that to find the derivative of the function, fx function, by limit, we use this formula, f prime x is equal to limit h goes to 0, f x plus h minus fx over h. So at this point, we have to look our function, this function. So again, we write limit h goes to 0, and fx plus h also is equal to c, and fx also c. So c over c is equal to 0. So limit h goes to 0, 0 over h, that is limit h goes to 0, 0. So there's no h here, and we have 0. So you see that the proof of rule 1 is okay. Now we prove it. Wherever c, whatever c is, that is 8 or pi over 2, or e or minus pi over 2, whatever is equal to 0. Now, let's pass to rule 2. Okay, rule 2. That is power rule for positive integers. Also, we will give the negative integer part, positive integers. If n is a positive integer, then d over dx, that's derivative of our function, and our function say x to the power n, our power is n here, is equal to n x to the power n minus 1. What we write here, that is, we subtract, you see, we subtract the power of n by 1, then put this n by multiplication on the left of the function. So we subtract 1 from the original exponent, that is, we have n here, and multiply the result by n. It says like that, we have this one, so we subtract 1 from the original exponent n, then finally we multiply the result with n. So this is the final result of derivative of the x to the power n. So for the examples, they are easy, but I try to give the easiest ones also. First, then maybe harder ones next. F of x is equal to x to the power 5 and f prime x. The question is this one. We say f prime x is equal to solution. We put x to the power 5. This is original exponent. We subtract by 1, and we put this original exponent on the left side and we multiplied it by. So it is 5 x to the power 4. Result is this one. Maybe another example. Now let's say t4 instead of x. We have t to the power 10 and f prime t is the question. So that is the solution. That is, we have d over dt, you see, and our function is t to the power 10, and we put 10 here on the left, and we subtract the original exponent by minus 1. So finally, the answer is 10t to the 9. Power is 9. Okay. Now next one, maybe rule 3. Next one is rule 3. It is constant multiple rule. Constant multiple rule. What I mean, that is, if u is differentiable function of x, and we have also c is a constant, then d over dx, and our function is cu. So we put our constant on the left, and we have to find the differentiation of u with respect to x. So the result will be like that. In particular, if n is a positive integer, so maybe we can say then or so, whatever, d over dx, I mean this one, x to the power n, and you see we put this constant c on the left and we multiply it with d over dx, x to the n, so that is c multiplied with n on the left, and we subtract the original exponent by 1. So this is the answer. So this is cn x to the n minus 1. Yeah. Now we can give examples also for that, for this one. Example is fx is equal to 1 over 3 x to the power 3, and the question is, of course, again same, f prime x, f of x, and maybe we can write also d over dx fx. And so what is the answer? Solution is f prime x is equal to, you see we have constant 1 over 3, we put this one on the left, and finally we have to find the derivative of x to the prime power 3. So 3 on the left, and we subtract by 1, 3 and minus 1. So finally we get x to the power 2. Yeah, it's easy again. Another example, this may be a bit different because I put e instead of a constant 1 over 3, x to the power e. So again, if you want to find the f prime x, or you know, d over dx fx, these are same, you know. So solution is f prime x is equal to, we put this constant e on the left again, and we put this e here, and we subtract again e by minus 1. So the final result is e squared multiplied with x to the power e minus 1. This is the answer of this question. Now another rule. Sorry. Yes, our fourth rule is rule 4, derivative sum rule. Derivative sum rule. So again, we have this definition. If u and v, we also, this sum and subtraction may be same on the same rule. I don't give any rule for the subtraction because they are same. You know, if we write like that, a plus b, this is sum of two number. But if we write like that, we can also do this one, a plus minus b. These are so as a sum of a function. So subtraction and addition are the same. If u and v are differentiable functions of x, then their sum, I mean u plus v, is differentiable at every point where, which points? These are the points where u and v, we can use v like that, not to mix with u and v, both differentiable. Yeah. At such points, the points I mean at every point, at such points, d over dx we have function like that, u plus v is equal to du over dx plus dv over dx. Result may be like that. Then we can give examples for this one, for this rule. Such as we have example like that, y is equal to fx, that is, question is, our function is this one, x to the power 4 and 12x. So dy over dx is equal to d over dx, x to the power 4, and d over dx, 12x. So finally, we know that we put this 4 on the left and we subtract one original exponent. So this one, first one is this one. And second one, for the 12x, we have to know that x has a power here 1. So we put this 1 here and we subtract again the original exponent 1 with minus 1. So finally, it is equal to 1 multiplied with x to the power 0, that is 1. So here we have 12 as a constant value. So we have a differentiation, derivative of x with respect to x is equal to this one. So finally, x to the power 3 and 12, 1 x to the 0, that is this one. Yeah, the result is this one. And I want to give another example with the power minus power. So sorry. So let's write a note for this one. This one. Our note is if we have fx is equal to x, f prime x is equal to, we have to think that we have a 1 here, a hidden 1 here. Let's say this is hidden 1 here. So we put this 1 here, and we put this 1 here, and we subtract 1 from here, and finally 1 multiplied with x to the power 0, that is 1. So another example, we have also, if we have here a constant value such as c, and c is also here, and c is also here, and c is also here, so maybe the solution is only c. And instead of c, if we have another integer, maybe 8, 5, whatever, this is like that, 8x. So f prime x is equal to 8. And another example by minus power, that is fx is equal to x to the power minus 2. F prime x is equal to, again, we put this minus 2 on the left, and we write minus 2, and we subtract by again minus 1. So minus 2 multiplied with x to the power minus 3. So result is minus 2 over x to the power 3. That is, we can see the function sometimes like that, 1 over x. And again, if you want to find the f prime x, that is, you see this is same as 1 over x, x to the power minus 1. So if you want to find the derivative of x 1 over x, or x to the power minus 1, that is, we write minus 1 here for multiplication. We multiply it by minus 1, and again we subtract by -1 as the original again exponent. So that is -1 multiplied with -2. So result is -1 over x to the power 2. You see it is -2, and we put on the denominator by 2 plus 2. Okay, now we have another example. So this example is derivative of a polynomial. Yeah, derivative. The polynomial is okay. Polynomial function. I think that I can write it as a polynomial function, but it's okay. Polynomial. Y is equal to f of x, that is x to the power 4 plus 4 over 3 x to the power 3 and minus 5x plus 1. Now we know that each of the item, to find the derivative of each of the items, so this is constant, and this is we can think as an x and multiply it with the constant -5, and we know the other ones. So dy over dx as a solution, and question is this one, y prime dy over dx or f prime x is equal to question mark, and dy over dx is equal to d over dx, this is x to the power 4, and plus d over dx 4 over 3 x to the power 3 and minus 5 d over dx x. We can write both this one or this one. You see I put this constant value 4 over 3 inside, and here I put this -5 outside of the function. You can write each of them, and here d over dx, we have 1 here. And finally, this is 4 x to the power 3. We have exponent 3, and again 4 over 3 as a constant. So we put 3 here, and we subtract the original exponent again 1, and -5. You see x is differentiation is 1. We know this one, and again here as a constant 1, we have derivative 0. So finally 4x cubed plus we have here 4x squared minus 5. Yeah, this is end of this solution. And another one, maybe we can stop here and don't forget to write the subject. We will continue with finding horizontal tangents. Don't forget this one. We will continue with for the 11th week with this one. How can we write? How can we find the horizontal tangents? If so, where are they? To find the place of the horizontal tangents, we have to find the derivative again. We are going to use derivatives. So this will continue. At 11th week. Okay. See you. Bye bye.